every bounded open interval AB of R is measurable. First implies second. Now we show second implies third, but second means inverse image of bounded open interval is measurable, and we need to show that this third means inverse image of closed subset of C is measurable. Okay. So second implies third. Now second implies third. Second means suppose F inverse of AB is measurable for each bounded open interval of R, for each bounded open interval of R. We show that inverse image of every closed subsets of R is measurable. We show that inverse image of every closed subset of R is measurable. So let's take any closed subset of R, then we need to show that inverse image of that closed subset of R is measurable. Let C be any closed subset of R. Now it's sufficient to show that F inverse of C, its complement is measurable. Okay. Then F inverse of C whole complement. Okay, let's find this. It's equal to F inverse of C complement. What C complement? C is closed subset of R. Therefore, C complement is open subset of R, and we know that every open subset of R can be written as a countable disjoint union of bounded open intervals. So it's equal to F inverse of union and runs from 1 to infinity A and B n. Okay, where A and B and they are all bounded open intervals of real line R, and they are also disjoint. Because this C complement, C is closed subset of R, therefore C complement is an open subset of R, and every open subset of R can be written as countable disjoint union of bounded open intervals of R. Now it's equal to union and runs from 1 to infinity F inverse of A and B. Now since it's given that inverse image of every bounded open interval is measurable, therefore this set is measurable. F inverse A and B is measurable. And we also know that the class of measurable sets is sigma algebra. So that means by sigma algebra we mean that it's closed under countable union. And now each F inverse A and B is measurable, and it's the countable union of these measurable sets, those measurable sets. And the countable union of measurable sets is again a measurable set. Therefore this set is measurable. This set is measurable, and which implies that since union n runs from 1 to infinity F inverse A and Bn is measurable as F inverse A and Bn is measurable is measurable for all n greater or equal to 1. So because each subset of X is measurable, so their union is also measurable. So therefore this is measurable. F inverse C whole complement is measurable. Which implies that F inverse C whole complement is measurable. The complement of a set is measurable. We know that a subset of X is measurable if and only if its complement is measurable. So if this set is measurable, its whole complement must be measurable. But its whole complement will be F inverse C, which implies F inverse C is measurable. So that proves a second implies third. Now we prove a third implies fourth. Third implies fourth. So this one was a second implies third. Okay. So let's prove third implies fourth. Third implies fourth. Third implies fourth. What's third? Third means so assume F inverse of C is measurable for each closure subset C of real line R. Okay, assume this. This is third. We show that this one F inverse it's A to infinity is measurable for all A belongs to R. So this we need to prove. But you can see this is closure subset of R actually, because it's closure on this side. It's a closure subset of R. It's actually unbounded closure interval. So on this right side, okay. So this actually since A to infinity is closed subset of R, so therefore since inverse image of each closure subset of R is measurable, so therefore F inverse A to infinity is measurable for each A belongs to R. Okay, that's third implies fourth. So it's actually obvious. Now let's prove 4 implies 5. 4 implies 5. So in 4 we assume that this one is our assumption. Assume F inverse A to infinity. F inverse A to infinity is measurable for all A belongs to R. Okay? Is measurable for all A belongs to R. We show that F inverse infinity minus infinity to A is measurable for all A belongs to R. So there will be different E's. So it's not this for this particular A, this is measurable. Whenever this one is measurable, it's not the case. So you can write here A and you can write here P for each P naught. Okay? So let's prove this. 4 implies 5. So 4 is given, we need to prove 5. Now this one, this is measured, it's given, so this is given, then So this one is measurable. We have this F inverse A to infinity its complement, which is equal to F. What will be its complement? It's actually the complement of this set. Okay, and that's equal to this one. It's equal to, what's the complement of this set? It's minus infinity to A, but it's open on this side. Okay, it's not closed. So we actually need to, it should be closed on this side. So we have this one. Since this is measurable, it's given in our statement. So therefore its complement is also measurable. This one is measurable. This is measurable. So F inverse of this unbounded open interval is always measurable. Minus infinity to A for each A belongs to R. This is true for each A belongs to R. So let's find this one. We need to show that this one is measurable. So now we calculate this one. Now, what's this? F inverse minus infinity to A closed here. So we try to find this set. Now you can see it's equal to, it can be written as this set, it can be written as F inverse this one. It's actually intersection and runs from 1 to infinity minus infinity to, it's closed on this side, A plus 1 by N. Okay, you need to verify this one. This is very simple, it's not too hard. You need to prove that this is subset of the intersection and intersection subset of this set. That's very simple. Okay, it's closed here. So first verify this one. Okay. So it's F inverse minus infinity to A closed. It's equal to F inverse. It's closed. Okay, here it's open here, not closed here. This one. Okay. So this is open here. So you verify this. Minus infinity to A closed. It's equal to intersection and runs from 1 to infinity minus infinity to A plus 1 when open on both sides. Okay. So this is very simple. Clearly you can see this one. Each one is subset of minus infinity to A, because if you choose any point here, it lies between minus infinity and A plus 1 over some K. So that means it lies between minus infinity. Suppose you choose any point B here, so that B satisfies the following property: minus infinity less than B less than A plus 1 by N. So which means minus infinity less than B less or equal to A. So that's here actually. Because if it's less than A plus 1 by N, then it must be less or equal to A, because it's true for each N actually. So letting N approaching to infinity, it's like this. If we choose any point here, then that point has the following property: minus infinity less than, if we choose B on this side, okay, it's like this: A plus 1 by N for all N. Letting N approaching to infinity, it gives minus infinity less than B less or equal to A. So that way it belongs to this interval actually. And conversely, you can see if any point is here, then it always sits in this intersection. So because it's less or equal to A, so whenever point is less or equal to A, then it is less than A plus 1 by N for each N. So this is simple. This you can do this one. Okay, it's now you can see this one. It's equal to here. So it's equal to here. So you can pull out this intersection from this function F inverse. It's F inverse intersection F inverse minus infinity A plus 1 by N. Now this is measurable because we know that F inverse minus infinity to A is always measurable whenever it's open on both sides. So this already you have seen that this one, it's F inverse minus infinity to A is measurable for each A belongs to R. This is measurable for each A belongs to R. So therefore minus f inverse minus infinity a plus 1 by n, because it's open. So instead of a we have a plus 1 by n here. So this one is measurable for each n. It's measurable. So is measurable. This and this set is measurable. Now since this f inverse a plus 1 by n is measurable for all n greater or equal to 1. So therefore the intersection of measurable sets is it's again measurable, because class of measurable sets is sigma algebra. So which means that this implies or you can say therefore intersection n runs from 1 to infinity f inverse minus infinity a plus 1 by n is measurable. But this one it's equivalent. F inverse minus infinity to a closed is measurable. So that's fifth one. 4 implies 5. 4 implies 5. Now we prove 5 implies 6. 5 implies 6. 5 implies 6. Okay. Five implies 6. So assume that this f inverse minus infinity a closed is measurable for each a belongs to R. It's measurable. It's measurable. So we show that inverse image of Borel set is measurable. Borel set is the more general than this one, because this in particular is also Borel set. We show that f inverse of B is measurable for all Borel subsets B of R. So this is Borel set. In particular, it's one of the Borel set. But every Borel set is not of this form. Okay. So we need to show that inverse image of every Borel set is measurable. Whenever it's given that inverse image of this particular Borel set is measurable. So how do we do this? We take the following class. So let's take this cursive A. Cursive A is the class, is the collection of following subsets for A belongs to R, such that f inverse of A is measurable. Okay, this is the class. So this class contains this element minus infinity to a closed, because f inverse of minus infinity to a is measurable. So then minus infinity to a, it belongs to cursive A, because the inverse image of this set is measurable, and it contains those subsets of R such that the inverse image of those subsets is measurable. And inverse image of this set is measurable. It's given in the statement 5. So it contains this set. Now next we see that this class is actually a sigma algebra. It's closed under complementation, and it's closed under commutable union. And it contains X as well, because it contains okay, let's so it contains whole R, because f inverse of R is whole X, and that's measurable because X is a major space. And then this R is also there. R also belongs to this set. Okay, and null set is also there, because inverse image of null sets inverse image of phi set is phi set, and phi set in X is measurable because X is a major space, and inverse image of whole space, whole real line R is whole X, and that's also measurable. because X has measured space. So it contains at least these three members. So next we need to show that it's actually a sigma algebra. So that's again simple. It's closure under complementation. So let's verify that this class is sigma algebra. So we first show that this cursive A is sigma algebra. So first we prove its closure under complement. Let A belongs to cursive A. This means F inverse of A is measurable subset of X. But class of measurable subsets of X is sigma algebra, so that means F inverse of A complement, which is equal to F inverse A whole complement, it's also measurable, is measurable. So which implies A complement belongs to cursive A, because the inverse image of A complement is measurable. So it's closure under complement. And next we see that it's closure under countable union. So let's take any sequence. Let A and B any sequence in cursive A. We show that its union is in cursive A. So, but it implies that F inverse of A n is measurable for all n greater or equal to 1, because each n belongs to cursive A. And this case, now since they are all measurable, so their union is also measurable. Union n runs from 1 to infinity. F inverse of A n is measurable. So this means F inverse union A n runs from 1 to infinity is measurable. So inverse image of this countable union is measurable, which means this countable union belongs to cursive A. Belongs to cursive A. So therefore cursive A is actually sigma algebra. It's sigma algebra. It's sigma algebra. So therefore A is sigma algebra. Is sigma algebra. So A is sigma algebra. Now this minus infinity to A, it belongs to A because it is sigma algebra, which implies its complement also belongs to A because of sigma algebra.